Hello everyone, I'm Swan Park and I'm going to introduce grasp and motion planning using learned geometric feasibility. First of all, the motivation is a grasp guide for cooperative manipulation. Manipulation problem usually includes grasping and motion planning. Because the grasp have discrete nature like right figure, integer search is necessary for solving the manipulation problem with such discrete grasp modes. But depending on the grasp mode, the motion planning can be infeasible as shown in the right bottom figure. The red line, a mode is infeasible because of the obstacles for all coparameter. But a blue mode is feasible with valid coparameter range. Moreover, considering cooperative manipulation, there are a considerable number of mode combinations. As shown in the background video, the furniture assembly have many discrete choices, and there are more combinations of the modes for multiple grasps. So we propose a feasibility estimator using a deep learning technique. The goal of this study is to find which mode is feasible when the object state is given. For the robot 2, the feasibilities are like the left figure. For the robot 3, the feasibility changes according to the robot base pose. By training a single model, it enables scalable feasibility estimation for multiple robots. The problem we want to solve with this feasibility estimator is the grasp and motion planning problem. The problem with multiple modes can be defined as a mixed integer programming. The state variable is robot and object configuration, and there's a set of modes and coparameters. Here, to solve the mixed integer programming, we need to choose discrete mode and solve nonlinear programming with the chosen mode. However, the total number of modes to search exponentially increases as the number of grasps increases. So we prioritize the mode search using geometric information. Geometric information is the object pose for reachability of the robot and collision information for accessibility of the object. This is the proposed model architecture that uses the geometric information. The model includes autoencoder to compress the nearby collision data. Then the encoded collision information and object poses are concatenated as an input of the fully connected layers. We'll refer these FC layers to LGF. The LGF learns the feasibility of each mode of the object. The proposed method can be used for multiple robots. The input object pose is with regard to the robot base frame, so learned feasibility for each robot can be obtained by transforming the global object pose to local object pose with regard to each robot base frame. After that process, just concatenating the outputs, we can obtain the mode feasibilities for multiple robots. And the proposed model also can be used to predict model feasibility for multiple states. For an example, pick and place problem have two configurations, start and goal. The LGF receives two different object poses and collision information, and by multiplying the predicted results, simultaneous feasibility can be acquired. This is the result of the trained model. The predicted feasibility is shown in the right figure. We'll show some experiments to demonstrate how the feasibility varies when an object moves in the given environment. As the object approaches to the robot, the top grasp mode feasibility increases. This demonstration is feasibility variation about the y-axis movement. And this is about rotational movement. These experiments demonstrate the simultaneous feasibility variation when the desired object pose slides left to right with a fixed start object pose. The top grasp mode had a high probability at first, but as it approaches the ceiling area, the top grasp mode becomes inaccessible. This is the quantitative result of the proposed model. We've compared grasp and pick-and-place problem with single grasp, multi-grasp, and multi-grasp with 16 threads. As you can see, the proposed model improved the search time for all experiments. This is the pipeline to demonstrate multi-states and multi-robot feasibility prediction for grasp and motion planning. 2 grasps are used to manipulate the furniture part with the 3 robots. The input is environment observation and the desired object pose. And using the proposed method, we obtain the mode search priorities. And using the priorities, the NLP is solved in order. This is a solution of a real-world experiment. And other feasible solutions are acquired by the proposed method for the given problem. The symmetric indicates the different orientation of the robot and the sector. This was the grasp and motion planning using learned geometric feasibility. Thank you for listening.